Okay, there's Peter.
I just see if Peter can hear you.
Okay.
I
Can
can
you
hear
hear
you.
me okay? Perfect.
Or is it just people are just zooming in?
I think people are just zooming in. I don't see Manoa Auditorium. Yeah. He got one very recently.
Very secret.
Only those who need to know, yeah.
Yeah, need to know basis, but he has one.
But he only used it for texting and calling. Yeah.
We can about page your phone. You have his number?
I know. Not a clue, no. Yeah, that was weird. He's really so punctual. He's so punctual. Let's see what it's like to my email before I was trying to send everyone, all the students a spreadsheet to fill out like into the email. And then he emailed me and I filled out my slot saying that, oh, can you change your time because something came up. So like, and I saw that email from later, so like I changed it in the spreadsheet. And I went to email him. And right before I sent my email, he said, thanks.
Maybe he got application when you checked.
But like, it was like less than 3 minutes between me writing the email and changing it.
Yeah.
They might be running. Says he's joining or he has joined.
Oh.
See him online?
He might. No. Oh, yes, he's online. Okay, perfect.
Fantastic.
There it is.
Yay.
We're waiting for you.
They more for stuck.
All right, aloha kakahiaka. Good morning and welcome to Rihan Zhang's dissertation defense this morning. My name is Christoph Bernick. I am her co-advisor with Mark Chun. How this is going to go this morning is that Mark and I will give a brief introduction to Suzanne's work that's a little bit different than what you normally will see. Then Suzanne will give a presentation which will last about hopefully 45 minutes. Then we'll open up the floor to questions from the audience, not the committee members. And then once we're done with questions, the committee and the candidate will move upstairs to a private session. We'll have refreshments outside down here so you can kind of hang out for a little while. And then eventually the candidate will come out. We'll have deliberations and celebrate after that. So I think let me get started with my brief little introduction here. So the reason we're doing this is that the candidate isn't necessarily going to put in all the sort of pictures that we want to show as advisors. So just to get started, so Suzanne joined the RoboAO team in 2022 in August, and the first thing we had her do was work on finalizing the alignment. In this case, it's a laser wavefront sensor for the RoboAO2 system, which is about to go to the telescope. So there she is working in the lab. We basically put her to work, so doing a lot of lab work. And this is very shortly thereafter. You can see Suzanne, Luke, Brian getting the instrument ready for shipping to the telescope. And there we are at the 2.2 meter, taking a look at Gemini. There's James with the infrared camera box. And here we are basically getting the instrument assembled on the telescope. So on the left, it got cut off there.
A little cut off.
Sorry, so Suzanne, this is Suzanne. She also got cut off on the other side. I apologize. I'm very sorry. That's not meant to happen. Okay, and then so we got the system on the telescope. This is James and Suzanne.
Oh, I
testing
know
it.
how to fix it. Sorry.
Okay, no worries. You can do that
There.
every slide. Okay, this is both of them. So we started to test the instrument in the end of 2022. It didn't work. Part of that was we had a faulty component, which was the breadboard for the adaptive optics system. So we ordered a new one as soon as we could. That's it on the left. So we basically stripped the adaptive optics system down to nothing. Got this new breadboard. There's just the DM there. And then Suzanne was responsible for repopulating the entire adaptive optics system and realigning all the optics and putting it together. So just 3 months later, there it is. Suzanne mostly has worked on the hardware. James worked mostly on the software, but they had this system ready to go. And so we were back up going to the telescope. In the meantime, we don't just do science or engineering or any of these other things. We do a lot of outreach as well. So all of us do this at the IFA. This is a group of us at the Merry Monarch Parade. So you can see Ellen, Suzanne, Doug, Carolyn, and Carolina on the end, as well as myself. So we had that was a sunny, hot day. And shortly thereafter, we were getting ready to take the instrument to the telescope again. This is Suzanne basically doing a little show and tell of RoboAO2 before we took it up to the telescope again. This is us going up. You can see the instruments packed up, getting off the truck, getting into the telescope. And here you can see the instrument on the telescope. Happy advisor, happy students, everybody's happy. This is what we like to see. And one last thing before I hand over to Mark. We do take time for personal events. So this is Suzanne having her birthday cake up at the telescope. And thank you, Luke, for bringing that one day. So we got to celebrate up there while we were working. So that was pretty cool. So Mark, I'll hand it over to you.
I don't have nearly as many pictures as Krista has. I apologize. But so I just want to highlight a few things about Suzanne that really were substantial and important to me here and to all of us. Suzanne's been here in Hilo since I think 2021.
Yes,
For
or 22, but I came in the summer of 21.
So the picture in the upper right is 2021.
Yeah.
I think. So it's just to harken back, she goes back a ways. The picture on the left is a picture of something called Friday Fun. We don't do enough of the Friday Fun. We have fun all the time here, but we were in the lab and I don't know if you know, some of us are working on these micro optics. They're sub-millimeter size optics. And we were trying to test one of the first pieces, and they're actually quite difficult to see. I can't see things. And so I was struggling to try to get things aligned, and Suzanne came to the lab and within minutes had everything aligned. And you can see this is the 4 people images from a pyramid using low micro optics. I just wanted to emphasize that she's here and she's part of all of our lives in lots of different ways, not just in their dissertation work, which is really great. On the adaptive secondary mirror stuff, this is a very fast project. This is kind of our celebration dinner that was at the S5 meeting in 2024. And very roughly, the order of people's efforts went along the back row and then along the right side of the table. So kind of the workflow went roughly that way. With Suzanne and Ellen kind of being the cleanup at the end. And so I really appreciate both of them being here because there was a lot of work that had to be done at the end. And it was I wouldn't say it was a stressful time. I think it was a really exciting time. Everything kind of came in within a couple months and everything had to be on the telescope within a couple months. And so there was a lot of work that was being done. And these are just kind of pictures of that last kind of period of between January of 2024 and April of 2024, we did a lot of different things. And including integrating everything in the lab, setting it up, and then getting the instrument ready for the telescope. All those things were done multiple times. And Suzanne was going through all these things. So I think you get a feel for, she's in the lab a lot, doing a lot of alignment, working with hardware, and she's very good at that. So I just wanted to highlight.
Thank you.
Okay, I think the rest is for you.
Okay, thank you for the very nice introduction. And now let's get started with today's talk. So thank you all for coming here today to attend my defense talk. My presentation will be focused on improving telescope performance with roboticized adaptive optics systems and adaptive secondary mirrors. To emphasize again, my advisors are Christoph Baranek and Mark Chen. And with the rest of the committee members being Rich Dekaney, Mike Liu, and Peter Sadowski. Before I begin with the rest of the presentation, I would like to acknowledge the two amazing teams that I had the privilege of working with. This work would have been possible without you. So first, the RoboAO team guided by Christoph, and including Reed, James, Luke, and Rachel, and the fantastic ASM team led by Mark with Ellen, Olivier Lai, Alan, Ryan, Mike Connolly, and our wonderful collaborators at TNO. Commissioning an instrument is never a solo effort. It is definitely a team sport. So I'm super grateful for all your help, support, and expertise along the way. Thank you. And now let's begin with the rest of the presentation. So as most people here are aware that the diffraction limit of the telescope is directly proportional to lambda over d, where lambda is the observing wavelength and d is the size of the telescope. This means that as we go to larger telescopes, we should be able to observe with finer details. Another metric related to the telescope size is the sensitivity. So when detecting faint objects that are background limited, the sensitivity is proportional to the telescope diameter to the fourth power, assuming the telescope is diffraction limit. So is this what we actually get? Unfortunately, the answer is no. And this is caused by our Earth's very own atmosphere, as very well depicted by the famous painting by Vincent van Gogh, The Starry Night. There are air pockets with different temperatures and therefore varying indices of refraction constantly mixing in the atmosphere, thus distorting the incoming light. To be more clear, here's an example of a diffraction-limited image. However, as the plane waves come from a distant point source, they get perturbed by the turbulent atmosphere, and the wavefronts become distorted, and therefore blurring the image of the star and making the resolution of the telescope greater than its diffraction limit. Also note how small the PSF of the seeing limited image is. It is smaller than half an arcsecond, and this is enabled by the superior seeing conditions atop Mauna Kea. So seeing limited PSFs are often greater than 1 arcsecond at many other sites. So how do we go from the seeing limited resolution back to the diffraction limit of the telescope? And voila, the answer is AO, or adaptive optics. Don't you worry, adaptive optics will help you solve your image resolution and sensitivity problems. Now I'll just give a very quick and brief adaptive optics crash course before diving into my dissertation work. And I'll focus more on the aspects that are relevant to my work. Adaptive optics systems are made with three major components. First, the deformable mirror that physically bends in shape to correct for the incoming wavefronts. Second, the wavefront sensor that measures the distortions in the incoming light. And the last but not the least, a real-time controller or computer that receives the measurements from the wavefront sensor and sends corresponding commands to the DM that corrects for the distorted wavefronts. All these components of the AO system often work in a feedback loop fashion with an operating loop rate of about 1 kilohertz to keep up with the constantly changing atmosphere. Another important element that enables the functionality of AO systems is the guide star or the reference source. We rely on it to learn how the incoming light actually gets distorted by the atmosphere. And there are two types of guide stars that we often use for AO in astronomy. The first is the natural guide stars, basically stellar objects. However, there's only a limited number of stars that are bright enough in the night sky that we can use as guide stars. Typically, most AO systems that use natural guide stars can only work with stars around 9th magnitude or brighter. And the guide star that you use cannot be too far off axis. The AO correction often breaks down when the target is a few tenths of arcseconds away from the guide star. Therefore, if we only use natural guide stars for adaptive optics, then the sky coverage is very limited to a few % of the night sky. And most stars are concentrated along the galactic plane, as you can see in this picture. So due to this limitation, astronomers developed artificial guide stars using lasers to increase the sky coverage of adaptive optics. And there are two common types of laser guide stars. First is the Rayleigh beacons that rely on Rayleigh backscattering, which takes place when the photons get deflected by the molecules in the air. The Rayleigh beacons typically operate at about 10 to 20 kilometers above the observatories. The second type of laser guide stars used is sodium beacons. These lasers emit photons that can excite particles in the sodium layer of the atmosphere, which is about 90 kilometers in altitude. The sodium beacons are a lot more expensive than the Rayleigh beacons, but they suffer less from the limitation of laser guide stars, given their higher altitude, which is known as focal anisoplanetism, or the cone effect. The focal anisoplanetism can be well explained by looking at the telescope and guide star geometry. So when observing an astronomical object, it is infinitely far away. So its light comes to us in a straight column or a cylinder. Whereas for a laser guide star, it is created within our atmosphere. Its light travels back to the telescope in a cone shape. So there are going to be residual turbulence outside the cone and above the laser guide star that we cannot sense. Additionally, some aberrations are also incorrectly sensed within the cone shape due to this projection effect. Because the cone and the cylinder don't really sample the exact same path of turbulence, there is only a limited amount of correction that can be done when using laser guide stars. Now that we know the basics of how an AO system works, let us also familiarize ourselves with the calibration and metrics that we use for AO systems. So in order for an AO system to function properly, a series of calibration routines must be performed. And the most important one is to measure the interaction matrix D of the system. The interaction matrix encodes the mapping between the DM actuators to the wavefront sensor subapertures. Specifically, it tells you how an actuator movement results in a certain wavefront sensor response. For example, let us look at a simple 2x2 Shack-Hartman wavefront sensor with an actuator configured at the center, known as the Fried geometry in adaptive optics. When you poke the actuator, it changes the wavefront and wavefront shape and moves the wavefront sensor spots away from their nominal positions, creating slope measurements in the wavefront sensor. And in most AO systems, the interaction matrix is measured by an internal calibration source. And just like the example that I've shown just now, we'd poke the actuators in the deformable mirror one by one while taking slope measurements with the wavefront sensor. So to perform the AO correction, what we actually need is going from slope measurements of the wavefront sensor to actuator commands, which is actually the inverse of the interaction matrix, known as the control matrix or the reconstructor of the AO system. Because the interaction matrices are usually not square matrices, so we normally use more Penrose matrix inversion or singular value decomposition to calculate for the control matrix. The most common metric to assess how well an AO system performs is the Strel ratio. It is defined as the ratio of the peak brightness in the measured image compared to the peak brightness that we would get from a perfect diffraction limited image. So in other words, a Strel ratio of 100% would be a perfect, theoretically flawless image from the telescope with no aberrations. And a Strel ratio of 0% would be a completely uncorrected, blurry image. Dynamical performances of AO systems also need to be assessed and studied. The frequency response function, or FRF, is a straightforward representation of the system dynamics. It tells you how signals of various temporal frequencies are able to be generated by the system and how they're modified transferring through the system. The frequency response function of a system is often depicted as a boat diagram shown here, which shows an example frequency response function of an AO system. The two components that make a boat diagram are the magnitude and the phase as functions of frequency. And let us try to wrap our mind around this idea by looking at signals at 1 Hertz versus signals at 100 Hertz. First, for a 1 Hertz sine wave, when it goes through the system, the signal preserves both its amplitude and phase given the magnitude is at 0 dB and the phase lag is at 0 degrees. So what goes in comes right out the same. However, when we look at a signal that's 100 Hertz, its magnitude gets decreased by 10 decibels, which corresponds to a 30% in the linear space. And there's about 180 degrees of phase shift. So looking at the input sine wave versus the output sine wave, the amplitude gets reduced to 30% of the input and plus a 180-degree phase shift. Based on this diagram, the AO system is able to create and thus correct for lower frequency signals, but the correction becomes less effective as we move on to higher frequencies. And indeed, this is what we see in the error transfer function, or ETF. So the error transfer function tells us how different frequencies of error signals are attenuated by the AO system. So consistent with what we see in the FRF, the ETF shows the greatest attenuation at the lower frequencies. And conversely, as we move towards the higher frequencies, the gain in the error transfer function increases, eventually surpassing the 0 dB line. This indicates that these higher frequencies are not being attenuated, but instead they're actually amplified. And the frequency at which the ETF crosses the 0 dB line is called the 0 dB bandwidth of the system, which is another common metric we use in adaptive optics. Typically, the higher the 0 dB bandwidth, the better the correction. Here's an example of the turbulence profile that we measure on SKY, which follows the Kolmogorov model. So it does show that most of the power lies within the lower frequencies. So knowing the frequency response of the function, we can design controllers to drive the system to maximize its performance and minimize the residual wavefront error. And so ultimately, our goal is to push the error transfer function curve to the right and suppress more of the lower frequencies. Woohoo! Congratulations on finishing your AO crash course. Now that we all have a brief understanding of how adaptive optics systems work and how they operate, we can finally dive into the main topics of my dissertation: roboticized adaptive optics systems and adaptive secondary mirrors. Traditional adaptive optics systems are often complex and expensive systems that require operational expertise. There's a large operational overhead that limits observations to just a few tens of high priority targets per night. They're also often housed in large premier telescopes with high demands. And additionally, the AO correction is generally limited to the specific AO instruments. So all of these reasons make adaptive optics inaccessible for many projects. Most telescope time is still seeing limited. Therefore, in my dissertation, I tackle these problems with two key technological advancements, which are roboticized AO systems and adaptive secondary mirrors. For roboticized AO systems, they can largely reduce the cost to operate AO systems and significantly increase observing efficiency. As for the adaptive secondary mirrors, because they get integrated into the telescope architecture, they are an ideal solution to provide correction for all instruments behind the telescope. For my dissertation, I commissioned two instruments that stand at the frontiers of these technology advancements in an attempt to bring the technologies to more mature states. And the two instruments are RoboAO2 and the IRTF ASM. And I will talk about each of them in greater detail in the following slides. So to emphasize why we want roboticized AO systems, first of all, once the AO operation is all roboticized, we'll have high observing efficiency and fast cadence to observe 200 to 300 targets per night. This allows us to conduct AO surveys that would conventionally take a large amount of telescope time. For example, we can quickly vet through test exoplanet candidates. There are about 5,000 of test candidates that still need to be vetted and confirmed. If we assume observing 250 of them per night with RoboAO2, it would only take us about 20 nights, whereas it would take about 170 nights with a conventional AO system that can go through about 30 targets per night. And additionally, with an intelligent queue system, we can respond rapidly to any transient alerts reported by the large all-sky surveys such as ATLAS, Assassin, and the forthcoming Rubin Observatory. For example, we just located a tidal disruption event about 2 weeks ago. And given these strong science motivations, I present you RoboAO2, the successor of RoboAO, which was the first instrument that demonstrated fully roboticized adaptive optics observing. So RoboAO2 is an instrument designed so we can easily make copies of for other existing small to mid-sized telescopes to improve their performance and keep them scientifically productive. Most of the parts are off-the-shelf components to keep the cost low and make the instrument easily replicable. We started the commissioning process of RoboAO2 in January of 2023. So I started populating the empty breadboard shown here with optics and cameras. I spent 2 months to fully assemble and align the instrument. So by March, the instrument was mostly built. Then in April, I finished off all the cable management and tested that each of the mechanical stages worked as expected. And eventually we went on to the telescope at the beginning of May of the same year. Here's a closer look at the interior of RoboAO2. The instrument seems pretty complicated, but I can simplify it as 5 main components. First, the telescope simulator has the internal sources that simulate a star and the laser guide star. It is a tool for us to perform internal calibrations of the system, and it also allows us to perform AO tests when we're not using the instrument with the telescope during the day. And the deformable mirror sits upstream of everything else to perform the AO correction. There's also a laser guide star wavefront sensor. There's a laser guide star wavefront sensor arm that picks up the UV light from the laser and sends the light into the laser guide star wavefront sensor camera that's right here. And the science arm gets the corrected wavefronts from our science target. There is a dichroic that sends the visible wavelength to the visible science camera right here. And the infrared light goes through the dichroic and gets sent into the Saphira camera that is mounted down at the infrared camera port. And there's also a natural guide star arm that picks up a part of the starlight to send to the natural guide star wavefront sensor camera that is right here. And whether we send light to the natural guide star wavefront sensor depends on what optic that we place in front of the science camera. So we have a moving stage that can put a beam splitter in that allows the natural guide star wavefront sensor to see the light. And the natural guide star wavefront sensor arm shares the same deformable mirror as the laser guide star system, which is readily available for conducting experiments for an adaptive optics method, HAPA, which I'll discuss in the following slides. So other than being a facilitized robotic adaptive optics instrument, RoboAO2 also serves as a demonstrator for the wavefront sensing technique, HAPA, which stands for Hybrid Atmospheric Phase Analysis. It is the idea to combine the use of a natural guide star and a laser guide star in an attempt to achieve higher strain ratio correction with fainter natural guide stars. This is enabled by the fact that laser guide stars can be used for higher order correction given it has more numbers of photons. But because the laser guide star performance is limited by the cone effect, we use the natural guide star to provide information about the lower order aberrations to combat the effect of the focal anisoplanetism, as shown in the simple diagram here. And because it is only for low order correction, we can use fainter guide stars. This method has been demonstrated once at the Starfire optical range back in the 90s by Ellerbrook and his team, but there was not further development as the team went into other directions. Then Palm 3000 restarted the study of this approach in attempt to expand its science reach for searching for exoplanets by going to fainter objects while maintaining the high Strel ratio correction. Unfortunately, there wasn't sufficient funding for this project with Palm 3000, and therefore we're studying it now with RoboAO2 to demonstrate it for the high contrast extreme AO projects on Mauna Kea, including SkexAO and GPy2. Here are the HAPA simulation results with the as-built RoboAO2 system. It is the resulting Strel ratio in R band as a function of the brightness of the natural guide star. So for a natural guide star only system shown in the blue curve right here, the brighter the star, the higher the the signal to noise ratio, and the lower the measurement error, and therefore better performance, so higher Strel ratio. Whereas for the laser guide star system shown in the orange curve right here, the performance is capped by the focal anisoplanetism. Therefore, when we combine the two systems, we should see improved performance with fainter guide stars. And indeed, this is what we see in the simulations. Oh, sorry. And the pink region here highlights the HAPA performance. That's better than both the natural guide star only case and the laser guide star only scenario. Note that our system only serves as a demonstrator for this method, so this region seems small. However, this improvement will be a lot more significant when implemented on systems with higher order and on larger telescopes. So in order to perform the HAPA experiments on Sky, I commissioned the natural guide star system for RoboAO2 since the subsystem was not commissioned when the rest of the instrument was commissioned. There are 3 necessary calibration routines that need to be conducted. They are making centroiding lookup tables, measuring slope offsets, and measuring the interaction matrix of the system. And I'll explain why we need to do these calibrations and how they're done in the following slides. And eventually, we had to test the system on Sky. So for centroiding, the accuracy of the center of mass centroiding algorithm in a Shack-Hartman wavefront sensor is fundamentally limited when the spot size becomes comparable to or smaller than the pixel scale. In this regime, the calculated centroid positions ceases to be a linear function of the spot's true position, which is the case for RoboAO2. So for example, let us look at this small diagram here. As the Shack-Hartman spot is translated across the cells, the center of mass algorithm's output is linear for only a very small amount of displacement. Significant nonlinearity emerges before the response saturates completely when the spot moves off of the left 2 pixels and fully into the right 2 pixels. This nonlinear behavior necessitates a calibration of the centroid response to accurately determine the Shack-Hartman spot positions. And therefore, we need to create the lookup tables for it. And that's how we take care of this nonlinearity. And also, the natural guide star wavefront sensor camera sees extra optics compared to the science camera. And therefore, there might be non-common path aberrations seen by the wavefront sensor that's not detected by the science camera. So the solution to take care of this non-common path aberrations is to use the internal light source to measure slope offsets on the wavefront sensor while keeping the deformable mirror flat to take out the non-common path aberrations. And lastly, I measured the interaction matrix of the system by pushing and pulling on the actuators sequentially while taking slope measurements, just like how I described it during the AO 101 session. And then we obtained the control matrix by taking the inverse of the interaction matrix. So we obtained the first light of the natural guide star system for RoboAO2 on the night of September 3rd, just a few months ago. This figure shows the best image that we captured that evening. It is a 3-minute exposure of 3 sig that obtained a Strel ratio of 37% in Z-band, and it achieved a contrast of 7.5 magnitude at 1 arcsecond of separation. We also compared the performance between the natural guide star system and the laser guide star system by observing the same target with both systems back-to-back to minimize seeing condition changes. And based on the mass measurements from that evening, this performance difference is largely accounted for by the focal anisoplanetism. This concludes my work with RoboAO2. I built and commissioned the instrument at the UH 2.2 meter telescope. I ran HAPA simulations and commissioned its natural guide star system in preparation for conducting HAPA experiments on Sky. In the future, we will implement Fast and Furious for focal plane wavefront tuning. And our team is getting the instrument ready for fully roboticized operation starting next year. We're going to integrate it with Robo88, which is a larger scale project to fully roboticize the UH 2.2 meter telescope to keep it scientifically productive and competitive against other larger and newer telescopes. We will also demonstrate HAPA with RoboAO2 on Sky, and we will use RoboAO2's wavefront sensor and science cameras to drive the UH 2.2 meter adaptive secondary mirror, which sets a nice segue to the next topic of my dissertation, adaptive secondary mirrors. So adaptive secondary mirrors are becoming more popular among observatories because they're integrated into the telescope. And this avoids having to have extra relay optics for the adaptive optics system, which reduces the thermal background. And therefore, this is ideal for infrared observations. And it may also provide correction for all instruments on the telescope. It is ideal for providing partial correction over a large field of view. And for how big the optic is, it is also the ideal deformable mirror to pack many actuators in for extreme adaptive optics. For example, if we look at the pictures on the right, it shows an image of one of the LBT ASMs, and each little circle is an actuator on the ASM. And it was able to make the beautiful point spread function down below with superior correction. However, despite how well the older generations of adaptive secondary mirrors performed, it's challenging to work with them due to the fact that they used voice coil actuators. The voice coil actuators only produced a force that's around 1 Newton. This drove them to use very thin phase sheets that were around 2 millimeters. And thin phase sheets meant that the ASMs were rather fragile and difficult to handle. Also, because of how small the force output was, the ASMs were using the nonlinear regime of the actuators. which necessitated the use of capacitive sensors to report the actual shape of these mirrors. And because how inefficient the voice coil actuators were, they had a large amount of heat output, which is detrimental to near-infrared observations and therefore required complicated active cooling systems. Therefore, working with TNO, our team proposed a new generation of adaptive secondary mirrors that use a new actuator technology named the hybrid variable reluctance actuators. Unlike the voice coil actuators that relied on Lorentz force, which is a force that's created when charged particles travel through an electromagnetic field, the hybrid variable reluctance actuators use force induced by reluctance instead. Reluctance is the magnetic equivalent of resistance for current. It is more efficient at creating force, and therefore these hybrid variable reluctance actuators can have a force output that's about a magnitude greater than the voice coil actuators. With the larger force output, we can go to thicker phase sheet, which makes the new adaptive secondary mirrors easier to handle. And there's no need for capacitive sensors since we'll be driving the adaptive secondary mirrors in the linear regime of the actuators. And there's also no need for active cooling. So given all these improvements, the new generation of adaptive secondaries are attractive. So if you were here during my dissertation proposal, then you might remember the small conversation that IRTF had with the UH 2.2 meter telescope. Initially, the UH 2.2 meter was getting the first adaptive secondary mirror using the hybrid variable reluctance actuators to go on sky as a proof of concept. But due to manufacturing reasons and the fact that the IRTF secondary mirror is only a third of the UH 2.2 meter secondary in diameter, IRTF actually became the first telescope to bring the new style of adaptive secondaries using the new actuator technology on sky. And therefore, the rest of my dissertation work is with the IRTF adaptive secondary mirror. So we started the commissioning process of the IRTF ASM at the beginning of 2024. The commissioning process of the system was very fast. We received the lab setup parts to test the adaptive secondary mirror in January. And then we received the adaptive secondary mirror itself in February. We performed a series of functionality tests and calibrations with the adaptive secondary mirror between February and March. And then in April, we successfully brought the ASM on sky and was able to close the adaptive optics loop with the system within a few hours of the first night. Next, I'll go into some of the details relevant to my work with the adaptive secondary mirror. So I designed and built a wavefront sensor and science package that drives the IRTF ASM. This package is used for both the lab setup and the on-sky configuration. In the lab, the R cube highlighted here is the light source of the system. It sends the light out to the ASM, and then the light comes back the same way and goes into our custom-built Shack-Hartmann wavefront sensor here, shown as a long tube. This is the wavefront sensor that drives the adaptive secondary mirror. We also have a Hassel wavefront sensor on the breadboard, which is a commercial high-order Shack-Hartmann wavefront sensor, and it is used in the lab to monitor higher-order aberrations that is invisible to our custom wavefront sensor. And the IR camera here serves as the scoring camera for our adaptive optics system when we go on sky. We also have a pupil imager in the system that can work in closed loop with the pupil steering mirror to maintain the registration between our wavefront sensor and the adaptive secondary mirror at the top of the telescope. In case if the telescope flexes significantly, slewing across the sky, the pupil steering mirror working in closed loop with the pupil imager would be able to bring that registration back. So using the setup, we characterized the performance of the IRTF adaptive secondary mirror. We studied the actuator step response of the IRTF ASM, which is shown in the figure here. We have the actuator amplitude shown in the y-axis and the time in the x-axis. So we can see that without using a fancy controller, it takes about 10 milliseconds for the actuators to settle into position shown in the solid curves. So to combat the slow actuator response, we know that a lead filter is needed in the controller to quicken the step response. What a lead filter does is that you can imagine, because these actuators have a lot of inertia to start moving initially, so the lead filter starts by pushing the actuators more than usual. Then it eases off on the push, and this forces the actuators to start moving quickly and settle into positions faster. In order to make lead filters that optimize the system's performance, we performed system identification routines to measure the frequency response function of the system in the lab. We did this by sending a white noise signal to one of the actuators and recording the wavefront sensor measurements in the meantime. And as people are aware that the power spectrum of a white noise signal is flat, so we characterize all signals at all frequency response of different frequencies at once. And based on the frequency response function, we designed different controllers that helped us to obtain optimal performance for the system. We also need to measure the interaction matrix of the system once the adaptive secondary is mounted on the telescope. And this is difficult because the adaptive secondary mirror because when the ASM gets installed on the telescope, its orientation or registration with respect to the wavefront sensor will definitely change. So we cannot rely on the lab measurements. And also, there does not exist a place where we can place an internal light source to help us perform this measurement. Therefore, we need to be able to measure the interaction matrix on sky using a natural guide star source under the presence of seeing. And given the slow actuator response, we realized that the original interaction matrix measurement method that we planned would not work because that method was called do crimes, and that relied on a very fast actuator response. And therefore, we developed a novel approach for these adaptive secondary mirrors called cacophony. This method is purely heuristic, which means that it does not depend on any models or lab measurements. It works by modulating the different actuators with various frequencies while recording the wavefront sensor measurements. Then by mapping the specific frequencies between the commands and the slope measurements, we know how the actuators are mapped to the wavefront sensor. The induced perturbations have stronger power than the atmospheric turbulence, and therefore this method works under the presence of seeing. Using an interaction matrix measured on sky using cacophony, we successfully closed the adaptive optics loop within a few hours at the beginning of our first night with the adaptive secondary mirror on IRTF. And here's a short video of the AO corrected PSF when we first closed the loop. And on the right, I am showing a 5-minute exposure of Arcturus or Hokulea taken during the first commissioning run. It has a straw ratio of 40% in H-band, which matches well with its expected performance. And that concludes all my work with the adaptive secondary mirrors. So far, all this work is motivated by making larger adaptive secondary mirrors with more actuators in the future for larger telescopes. Therefore, we'll further test the calibration routines developed in this dissertation for larger adaptive secondary mirrors, starting with the UH 2.2 meter adaptive secondary, which will have 200 plus actuators, and then eventually implement them for the Keck adaptive secondary mirror that will have about 3,500 of actuators. So to sum up my dissertation, I built and commissioned RoboAO2. I conducted HAPA simulations for it, and I commissioned its natural guide star wavefront natural guide star system. And with the IRTF ASM, I commissioned the instrument, designed and built its wavefront sensor package, studied its dynamical performance, and developed a novel approach to measure its interaction matrix. So I hope that these two instruments can be valuable prototypes to other observatories that either want to be roboticized or get adaptive secondary mirrors. And this sums up my presentation, and I would like to give special thanks to people that have helped me along this challenging but rewarding journey. First and foremost, thank you, Dad, for teaching me the scientific mind since I was a young child and installing the seed of curiosity in me. Thank you to Mark and Christoph for being my shining beacons and holding my hands through this journey. Thank you to Rich, Mike, and Peter for being a part of my committee. All your comments and suggestions have been extremely helpful. Thank you to all my distant collaborators who have helped me along the way, especially Olivier Lai, Reed Riddle, Max Baton, and Marcos Van Dam. And a special thanks to Mike Connolly, who gave me a lot of support when I was very stressed out. And thank you to all my IFA friends, especially Casey, Rena, and Ellen, who made me not lonely. And shout out to the IFA Hilo grads who shared precious moments with me in the IFA Hilo courtyard and during coffee. I would also like to give special thanks to the admin, especially Sandra, Mapuana, Cindy, and Alyssa for helping me with all my paperworks. Additionally, thank you, Luke, and the 88 crew for supporting me through all the days and nights with the UH88. Also, thank you to the IRTF and the crew for supporting us through the IRTF ASM work. Unfortunately, I cannot list all of the people that have helped me along the way, given we have limited time, but know that I deeply appreciate all your help and support. Thank you so much to everyone who have given me strength during this long way. I would not be here today without all your love and support. And now I'm open to take any questions.
All right, questions from the audience? All right, Ellen?
Yes.
So your talk was really good. In your atmospheric turbulence plot from the telemetry,
Yes.
it had these like two really big spikes in it.
Mm-hmm.
Do you know where those come from?
Let me go back to. Yes, so this comes from a open loop measurement that we took with when we were working with the IRTF ASM. We have not identified what could have caused those big spikes that we see, but it could very well be telescope vibrations or just other vibration sources that sits within the dome or within our instrument. But we have not taken the time to identify exactly what caused them. Yes,
Yeah.
Guillaume?
In the RTF ASM bench, you guys have two waveform sensors. And can you tell us more about this? Like, do you use them simultaneously? Or what's the purpose of each,
Okay, I guess I should repeat your questions for Zoom land. So. Okay, the question was, can I explain more about how the wavefront sensors are used and why there are two of them on the board? So yes, good question. For our custom built wavefront sensor that's shown in this long tube right here, it's a 12 by 12 Shack-Hartman wavefront sensor, so it can only sense the lower order aberrations. But because we were commissioning the instrument, we were worried that there might be higher order stuff that cannot be seen by this 12 by 12 Shack-Hartman. So we installed the Hassel wavefront sensor in there, which allows us to see 47 by 47 sub-apertures, which has much finer spatial resolution compared to the 12 by 12. And the Hassel wavefront sensor is really only used in the lab. We haven't really used it on Sky, but the 12 by 12 Shack-Hartman is what we use to drive the adaptive secondary mirror. Good. Yes.
You mentioned that do crime would not work well with the temporal lag of the temporal response of the SM, but cacophony would. Can you explain why there is that difference?
Yes, so how do crime works, to really explain how do crime works is that you are constantly sending a white noise signal to the actuators, and when you sample for long enough and you know how you're commanding the actuators versus the wavefront sensor output, that's how you disentangle the interaction matrix of the system versus the atmosphere. So that basically relies on the actuators to move into the commanded positions immediately. But because, like I showed, that the actuator response of these actuators are slow, so that's why we went to cacophony. And cacophony works because you're just constantly sending a sine wave to the actuators. And then by taking the Fourier transform of the wavefront sensor response, it doesn't really matter how much lag there is between the actuator versus the wavefront sensor. Like, you're still gonna pick out that frequency of signal. So really quickly, since you're asking about do crime. So to combat that situation for do crime, for the actuators not reaching into position immediately, we actually tried this modified do crime method we for now call lagging do crime. And what we do is we stay in position for a bit longer after each commanded positions. And then we take the wavefront sensor response of a number of steps afterwards, so that there's time for the actuators to get into position. And this lagging do crime method actually worked reasonably well. And here's a comparison between the interaction or the control matrix that we would get with cacophony versus the lagging do crime method, and they're largely the same.
Okay, thanks.
Yeah. Thank you. Any other questions in the room?
Check
Yes.
one.
Nor?
Thank you. That was a really great talk. think on slide 60 or 61, you had the HAPA comparison between natural gate star and laser gate star.
Yes.
And looking at the swell ratios here, and I was wondering if you had any ideas of how the HAPA regime could be improved and how different would it be on different types of instruments, especially on extreme AO type of instruments.
Yeah, so with extreme AO instruments and given those are really nice instruments, they'll be housed on larger telescopes. You would see this the HAPA profile should drag out further so that this pink region would grow this way. And in addition, this was done for only a 16x16 order instrument, but we can go to higher Strel ratios if we go to higher order systems.
Okay, so the higher the orders, the more the HAPA regime gets better, bigger.
Right. Yeah. And also the larger the telescope, this curve should move to the right.
Okay.
Yeah.
Thank you.
Yep. Thank you.
Are there any questions online? Can you see anybody raise hands?
Let me take a look. I'd have to stop share if I try to look at.
If there's anyone online that has a question, if they can.
Maybe
turn the
raise
video
your,
on, then ask the question.
yeah. Or maybe they're not allowed
They
to
might
do
not be
that.
able to.
Yeah, okay. Let me stop share here
Yeah.
and then look at if there are questions. So far, no one has posted any question on Zoom land.
Okay, any other questions here? Going once, going twice. Okay, let's thank Suzanne again.
So committee members can stay online on Zoom. Suzanne,